Mr. Eck here, welcome back. Now we're going to look at geometric series. Remember, series is our word for when you take a sequence and you add up all of the terms of that sequence. So we're looking at geometric sequences, which are things which have a constant common ratio, but now we're going to start adding up the pieces. There are two types of geometric series, finite and infinite. Finite looks like this: 2 plus 4 plus 8 plus 16 plus 32, and this is something you could, hypothetically at least, compute on your calculator. Now, we're going to be wondering, hey, is there a formula for this? Because what if there aren't, 5 terms? What if there's 1,000 terms? Can I do this in a simpler way? And it turns out the answer is yes. There is a nice formula for the finite series. But probably more interesting are the infinite series. Is it possible that something like 1/2 plus 1/4 plus 1/8 plus 1/16, etc. could have a finite value? We know with arithmetic series, there's no way that an infinite series can ever add up to a finite value because the terms keep growing. But with geometric, we have this interesting idea that the terms seem to be shrinking. So you might wonder, like, hey, could this ever reach a single finite value? And it turns out the answer is yes, and that's very interesting. This might take 2 videos. I don't know at this time. We're just going to start talking and see where we end up. Now, in the past, I've given you a example first and then developed a formula. In this case, we're going to give you the formula right away because it is pretty complicated. So, the sum of the first n terms of a finite geometric series, so that's what we mean by the first n terms is finite, is always given by a1 times 1 minus r to the n all over 1 minus r. Remember that a1 represents our first term and r represents the constant ratio. By the way, of course, needs to not equal 1 and not equal 0 because those would both be very, very boring types of sequences. But as long as that's true, then this will actually always work. And we could do this in an example, but I'd actually rather just show you the proof right now. We're going to use Sn here to stand for the sum of the first n terms of the series. And actually, the first step in this proof is just writing out what that sum actually is. So it would be the first term plus the second term is a1 times r, the common ratio. The term after that is the first term times the common ratio twice, a1r squared, plus a1 r to the third, plus, now I'm going to skip a couple terms, and then I'm going to write out plus a1 r to the n minus 2. So I'm getting to the end here, and then plus a1 r to the n minus 1. And remember, the general form here has an n minus 1, so this is actually the last term because there was no r in the first term. So that's why I'm ending at a1 r to the n minus 1. That should be the sum of the first n terms. I've added all those terms up. That's what those plus signs are doing. Now, I'm going to take a second copy of this very sequence, stick it right underneath the first one. I've actually shifted it over slightly because I'm about to do something sneaky. I'm going to take this second copy and multiply it by the common ratio r. And I have multiplying across a sum, so I have to multiply that to every term. So that'll be like r(a1). a1r becomes a1r squared. a1r squared becomes a1r cubed. a1r cubed becomes a1r to the 4. a1r to the n minus 2 becomes a1r to the n minus 1. And a1r to the n minus 1, I multiply that by n, becomes a1r to the n. So I've multiplied everything by a factor of r. I'll just circle that to show that what I did there. Now, we're going to subtract the terms of the 2 copies of the sequences. So we'll just take this whole second sequence and subtract it from the first one. So that'll be like doing Sn minus r times Sn, which we'll simplify in a second. And then let's actually see what we get. So a1 doesn't have anything that matches in the bottom, so that will be a1. But a1r has an a1r in the bottom, and those are going to reduce out. And a1r squared has an a1r squared in the bottom, and those will reduce out. So will those. This one I didn't write it, but it would have something that reduces out. everything would have something that reduces out, right? Somewhere in there, even if we didn't write them all. Those would go out. The n minus 1s would go out. The only thing that would be left is a1r to the n. So I'd have a1 minus a1r to the n. Well, this still kind of looks like mathematical nonsense, but wait. What are we trying to solve? Well, we're trying to find a formula for Sn. And I have now two Sn's. We can turn them into one Sn, just like this. Factor it out. Sn times 1 minus r. And let's factor that a1 out of the top. So a1, 1 minus r to the n. Now, we just have to divide by 1 minus r and get that Sn, the nth partial sum of the sequence, is equal to a1, 1 minus r to the n, divided by 1 minus r, the formula that we were given at the start. Now, do you need to be able to reproduce this proof? No. I just personally find it more satisfying when I have a complicated formula to know a rough idea of how it's proved, even if, you don't reproduce the steps every time. It's nice to say, okay, I know that comes from taking two copies of the formula and kind of making them almost collapse like a telescope or something, and then arriving at this solution. That way, if you do forget the formula and you have it a little bit of time, you can actually rederive it from scratch if you need it. I'm just going to let that formula hang out at the top of the screen there, and let's do an example. Let's find the sum of the first 12 terms of a geometric sequence. So this has ... but I'm finding just 12 terms, so this is finite because I'm only finding 12 terms. So I'm looking for basically S12. Well, I need to know the first term and the ratio. Now I know the first term, that's 8, that's A1. To find the ratio, I need to do the two consecutive terms divided by each other. So, like an over an minus 1, but we can take any two terms in this sequence as if we know it's geometric. So we could do negative 24 divided by positive 8. That ratio is negative 3. It looks like we're multiplying by negative 3 every time as we go up. And at least when I first did this, I thought, man, this is a really nice formula and everything. Is it going to work with a negative ratio? The answer is yeah, it still does. That's one of the really nifty things about this whole thing, is it works. Whether your ratio is positive, negative, whatever it is, it's still going to work out. So I know what R is, I know what A1 is, so I know that S12 should be given by the formula A1, which is 8, times 1 minus the ratio, which is negative 3, to the 12th, because I'm looking for 12 terms, divided by 1 minus r, so that'd be 1 minus negative 3. At this stage, because there's a 3 to the 12th, we are going to go to the calculator, but we're just going to type this in using like good math notation and a lot of parentheses and see what we get. All right, I've typed that all in. Really be careful if you do have a negative ratio that you put parentheses around that negative number. Otherwise, the calculator will not interpret it correctly necessarily. It might, but it probably won't. All right, this is our answer, negative 1062880. That's negative 1,062,880. And you're like, wow, that's a really small number, or a really big number, but negative. Wow, why is it so negative? Well, think about it. We're going to the 12th term, and it probably is just that the 12th term is a negative number, since all of the even-numbered terms, right, the 2nd, the 4th, the 6th, the 8th term, those will all be negative numbers, so the biggest number we're adding on is itself negative, which means the whole sum of all of those numbers, positive and negative, is going to be negative itself. And we could test that theory, since we've typed the formula in. Maybe look at the 13th term. So that should be able to just switch that to a 3. And that should be a really big positive, because the 13th term would be a really big positive number. Adding that on to a pretty big negative sum is still going to be a pretty big positive number, and it is. So that seems like our formula has worked out. Here's another way that we can check our work. Remember your sigma notation, right? This is a sum, so we can write it using our sigma notation. So we could write this as the sum. We have to pick an index, so we could say from I equals 1 to 12, And then we need to think about what formula would go in here. Well, could I just use the geometric series formula? 8 times negative 3 to the I minus 1. I need to do a minus 1 here because I'm starting with 8. So I need to start with 8. So I need to have an I to the 0 as the first term. And that will give me 12 total terms. That's sigma notation. We can type that into the calculator too, and hopefully we'll get the same result. Let's see. Just to spare you the pain of typing in the sigma notation, you type it in, you get all your parentheses in the right spot, and you get the same result. And just by way of remembering, if you need the sigma notation, you can go to alpha, F2, select option 2. That'll get you your blank sigma, and then you can put everything in. Just be sure you use a lot of good parentheses to make sure your calculator is interpreting the result the way you expect it to. So that works out. We get the same result. All right, next example of a finite geometric series. What if we had to go backwards from sigma notation, right? We're given one of these sigma things. Let's see if we can interpret it. So the first thing to identify here is that our index I is starting at 0 and going up to 15. If you think really carefully about this, from 0 to 15, that's actually going to be 16 terms. So when we think about n, that's going to be 16. You always have to check both indices, especially for things that start at 0. You can't just look at the number on top. Let's go ahead and write out what the terms would be. So if I equals 0, then the first term would be 1/2 times 3 to the 0, which is just 1/2. Then when I equals 1, that'd be the second term. There would be 3/2. When I equals 2, that'd be 9/2, etc. So it looks like we're going 1, 3, 9, except everything's divided by 2. So we'd have 27/2. We're multiplying by 3 every time. Then all the way to the end, well, we'll just have whatever 3 to the 15 is divided by 2. I really don't want to add that up by hand, but we have a formula. So the formula is a1 times 1 minus r to the n all over 1 minus r. In this case, a1 is 1/2 and r is 3 and n, like we talked about, is 16. So I'm going to plug all those things in. It'll be 1/2, 1 minus 3 to the 16th over 1 minus 3. And again, we just crunch this into a calculator and see what you get. All right, so I put it all in. We get a very large number, but of course that should not surprise you. 107,616,80. That we are looking at something in the 10 millions, 10,761,080. Big number, but because we're adding up things and 3 to the 15th is very big, the fact that we're dividing by 2 isn't really going to change much. You can check your calculator sigma notation also. Same deal. Same number. By the way, if you're using I in the calculator, don't use the little I down here. That's the imaginary unit. Use the I that you get from doing alpha x squared. That's the I you want. You can also, I find that kind of deeply uncomfortable. You can also use k as your index of summation if that's easier. One closing question. Why does the ratio need to be not equal to 1? I mean, we don't understand why it can't be 0. Why can't it be 1? Well, think about it. What if the ratio is 1? Then you just have the same term over and over again, and the sum is not going to need any kind of goofy convergence. You're just going to have, n copies of that sum. So that's why we need a ratio that's not 1 or 0. All right, to close us out here, we're going to stop and do a breakpoint. These are finite geometric series. They have a complicated formula that looks like this. We saw how you prove it. We saw how you apply it. And again, these problems can get more complicated depending on what's given and what's missing, but the information will always be there. You just have to think carefully about what do you know, what do you need, and how do you solve for it, and you'll be able to find everything you need. Stay tuned for the next one, and we'll talk about those infinite series and how they could possibly behave.